Okay, in this screencast we're going to talk about gravitational potential energy at astronomical distances. Before I get into the equation for that and a little explanation of it, I want to first kind of stress what our gravitational potential energy formula is when you're near the surface of the Earth. So Eg, which again is the same as Ug in your textbook, is equal to mg times h. Now, if I'm talking about change in gravitational potential energy, then we use, a change in height. Now, I want to talk a little bit about why the reference point for gravitational potential energy is arbitrary and it really doesn't matter. All that matters is the change in gravitational potential energy. The example I'm going to use is a ball on top of a cliff that is 5 meters tall, and we'll just say the mass of the ball is 1 kilogram. And the ball is going to get pushed off the cliff and it's going to land at the bottom. Now, if I had my pie chart, remember the pie graphs that we were using before, and we had one here, we'll call this point A and we'll call this point B. So this is my pie chart at A and this will be my pie chart at B. B is just before it hits the ground. So at B, the velocity is non-zero. So it hasn't touched the ground yet, it's still moving. So I think we could all agree that when it's at A and it's at rest, all of its energy is in the form of gravitational potential. Down here at B, all its energy just before it hits the ground, assuming that this is my reference point for Ug. So at the ground, my gravitational potential energy would be 0. That means all my entire pie would be kinetic energy just at the instant before it hits the ground. So I think we agree on that. So all of the gravitational potential energy has been converted into kinetic energy. Let's say, as I showed here, that the gravitational potential energy is 0 at the ground. That means the Ug at the top, I should be consistent and use A. Gravitational potential energy at point A is mg times the height at A, which is 1 times 10, I use for g, times 5. That's 5 meters above the ground, so that's 50 joules. Obviously, Ug at point B is 0 by definition. So the change in gravitational potential energy is final, which is Ub, minus initial, which is Ua, which is 0 minus 50, which is negative 50 joules. Notice I've lost 50 joules of gravitational potential energy. That's gone into kinetic energy, which has gone from 0 to 50. So that same 50 joules of energy is now in the form of the energy of motion, or kinetic energy. Look at what it would be if I, instead, for the second scenario, let's say I call Ug 0 at the top. And I'll show you that it doesn't matter when you talk about change of Ug what you call 0. Now at Ug at A, let's make a demarcation here. Ug at A is 0 by definition in the second scenario. The gravitational potential energy at B is equal to the mass times little g times the height is now negative 5 because I'm below the 0 point. So if this is my 0 point right here, I'm 5 meters below it down here, this would be negative 5. So I have negative 50 joules of gravitational potential energy at point B. So it is possible to have negative gravitational potential energy based on where you choose your reference point. So now my delta Ug is still final minus initial equals negative 50 minus 0, still negative 50 joules, just like it was before. So it's exactly the same change in gravitational potential energy regardless of where my 0 point is. So that 50 joules of gravitational energy has been converted into all kinetic, as you see here. Okay. Hopefully that makes some sense to you. I don't know why it doesn't undo my last action. Anyway, I didn't mean to scribble out the K, I just meant to show that's the pi that's now completely kinetic energy. Alright, so now with that background, we're going to talk about gravitational potential energy at astronomical distances. And when we look at the formula for gravitational potential energy at astronomical distances, the thing that's changing, and I'm gonna say, I'll write the formula out here. The formula looks like that. And let's explain what some of these terms are. I'm assuming that I want to find the gravitational potential energy of an object, maybe a satellite, that is orbiting the Earth. So I've got the masses of the two objects involved. The mass of the satellite is this one right here. Let's say it's a satellite. And then I've got the mass of the Earth. R is the center to center distance. And G is that universal gravitational constant that we saw before, that is negative, or I'm sorry, 6.673 times 10 to the negative 11th, and there are some units there that make the in the gravitational formula the units come out to newtons. Okay, don't worry about the units of that. The units of UG will be in joules still, that doesn't change. The reason that it's a different formula for things that are at astronomical distances is that when you're close to the Earth, this formula here, my value of little g changes. It starts out at 9.81 meters per second, close to the surface of the Earth, and even on Mount Everest, it's about 9.78. So anything terrestrial, including the highest point on the Earth, Mount Everest, is very, you can use the MGH without too much error in your calculations. But when you talk about 200, 300, 400 miles and more above the surface of the Earth, now you have to consider the fact that little g changes and gets smaller as you go further away. Now I can't derive this formula for you because it requires calculus. Okay, so I will just explain, first of all, try to explain why it's negative, because there is a negative sign in front here that you notice right there, and there's a reason for that. Because we know, let me draw a little picture of an Earth here. Let's make it blue. All right, let's say, I'm a certain distance away from the center of the Earth. I'll call this RA, and I move to a greater distance from the center of the Earth, RB. Okay, notice that the R is in the denominator of this equation right here. So the further I get away, the smaller the negative number is. So this is a smaller negative number further away, and this is a larger negative number closer. Okay, so when you talk, let's say I go from A to B. Okay, so this is initial, and this is final right here. B is the final. So when you talk about delta UG, it would be the amount I have at B minus the amount of energy I had at A. You would expect that I would be gaining gravitational potential energy the further I get away from the center of the Earth, just like I do with MGH. The higher you are above the surface of the Earth, the greater the gravitational potential energy that the object possesses. So likewise, you would expect something that's further away out here, out at that point right there, to actually have greater gravitational potential energy. So look what happens when I go from A to B. I have a smaller negative number minus a large negative number. So minus a large is like adding it. So this is going to work out to be a positive value. So I'll actually gain gravitational potential energy by going from here to here. I know it's a little bit confusing because of the negative sign, but it turns out it's the only way using this formula right here, the one that I circled in red a second ago, the only way to get a gain in gravitational potential energy when you go farther away from the center of the Earth is to have that negative sign in front. So that's why it's there. Don't let it confuse you. Okay, so our formula for gravitational potential energy, I'm going to have that capital ME, I'm going to assume it's a satellite orbiting the Earth. So I'm going to have M S is the mass of the satellite, and R is going to be the center-to-center distance. What I'm going to do is I'm going to work a problem here, an example problem, with a satellite, an imaginary 200 kilogram satellite that's orbiting at 400 kilometers above the surface of the Earth, and then it's going to come down to about 300 kilometers above the surface of the Earth. And we're going to look at the change in gravitational potential energy of that. I'm going to do this offline, and then I'll explain what I did after I come on, so you don't have to watch all of the details of me writing on the slate. Okay, a lot of writing here, so let's try to go through this. Here's the equation we started with right here. So if I am talking about a satellite that has a mass of 200 kilograms, initially it was 400 kilometers from the surface of the Earth, and then later it comes down to 300 kilometers. Notice since it's a center-to-center distance, I have to add the distance to the center of the Earth, so I have to add that 6.37 times 10 to the 6th. Over here, I've got my formula. The change in UG is final minus initial. So my final would be, the negative sign is in the formula, so that's there because it's in the formula, and I have the final radius minus the initial. Since it's minus the negative, I have a plus, and there's the initial radius in the denominator. Well, basically, I can factor out everything in the numerator. The mass of the satellite, the mass of the Earth, the negative sign, all those things can factor out. So I have down here, I've got, there's G, there's the mass of the satellite, and there's the mass of the Earth. I factor all those things out. So in the parentheses, I have 1 over RF. So this is 1 over, that's R, the final distance away. Notice there's the 300,000 kilometers. And then initial radius, where I start from, I started 400,000 kilometers away. So that's the formula right there. I'm going to go offline and I'll calculate an answer just so you have an idea of what the change in gravitational potential energy is. Okay, the answer I get is the change in gravitational potential energy is 1.76 times 10 to the 8th joules in my example. Now I know there's a lot of stuff here. There's a lot of numbers, so I don't want you to get confused by that, but it's actually a negative. I'm sorry, I should have had a negative sign in front of that, because it is, I've got the negative sign here in the formula, and I'm going to have a positive number coming out of these parentheses over here on the right. So you end up getting a negative answer, because as I get closer to the Earth, I lose gravitational potential energy. So all of that gravitational potential energy, if this was if the satellite that we're talking about was moving closer to the Earth, it would gain speed, gain kinetic energy moving closer to the Earth, much like dropping a rock from a higher distance or from a higher level above the surface of the Earth. It gains kinetic energy as it falls closer to the Earth. So this makes sense, because I'm losing gravitational potential energy when I move closer to the Earth, in this case from 400,000 to 300,000 kilometers above the surface. So that brings up an interesting thing. I'm going to show you real quick how to calculate something called escape speed. Now, this is probably not going to be on the AP exam, so if you don't want to watch the second half, you don't have to, but it's very interesting to calculate the escape speed of an object to completely leave the gravitational. You know what I'm going to do? I'm going to put this on a separate screencast, so you don't get intimidated by having a 20-minute long screencast. I'm going to do a second screencast with the escape speed for a rocket to leave the gravitational attraction of the Earth, and it's related to what we've just talked about. Okay, we'll talk about any questions you have on this tomorrow in class.